today on Trigonometries, we're going to do an example that concerns continuity. In particular, we're going to try to find the value of k that makes the following function continuous at x equals 2. It's a piecewise function where f of x is equal to x squared plus 1 whenever x is less than 2. It's equal to x cubed minus 3 whenever x is greater than 2. And it's equal to k when x is equal to 2. And we're supposed to define k to make f continuous at x equals 2. Well, in order for a function to be continuous at a point, the limit of that function as x approaches that point has to exist, and it has to equal the value of the function there. The value of the function is simply going to be just k, that's f of 2. But in order to figure out what we need to define k to be, we need to also know what the limit of the function is as x approaches 2. Now for the limit as x approaches 2 of this function to exist, it has to approach the same value as x approaches 2 from the left as when x approaches 2 from the right. Since this function uses a different formula when we're on the left of 2, when x is less than 2, compared to when we're on the right of 2, or when x is greater than 2, we need to compute these limits separately to make sure that they actually equal the same thing. Computing the limit of f of x as x approaches 2 from the left, we get that the limit as x approaches 2 from the left of f of x has to be equal to the limit as x approaches 2 from the left of x squared plus 1. And the reason why x squared plus 1 is the right term here is because that's the value of f of x when we're to the left of 2. When x is less than 2, x squared plus 1 is the formula for f of x. And so that's what we're going to use when we compute the limit as x approaches 2 from the left. Well, that's just a polynomial. And when you compute the limit of a polynomial as x approaches any number, you just simply plug that number into the polynomial. And so here we plug 2 into the polynomial x squared plus 1, and we arrive at 2 squared plus 1, which is equal to 5. Now let's compute the limit as x approaches 2 from the right. To the right of x equals 2, f of x is equal to x cubed minus 3. And so when we compute the limit as x goes to 2 from the right of f of x, we compute the limit as x approaches 2 from the right of x cubed minus 3. Again, this is a polynomial, and so we can simply just plug in the x equals 2 in order to compute that limit. And this equals 2 cubed minus 3. 2 cubed is 8, 8 minus 3 is 5. And so the limit as x approaches 2 from the right of f of x is equal to 5. But that's also what the limit as x approaches 2 from the left of f of x was equal to. And so the limits as x approaches 2 from either side both agree, and that means that the overall limit as x approaches 2 exists and is also equal to 5. Well, for f to be continuous at x equals 2, we have to have the function value equal the limit at that point. So the limit as x goes to 2 of f of x has to be equal to f of 2. But f of 2 was just k, and here the limit as x approaches 2 of f of x is equal to 5. And so the value of k that will make f continuous at x equals 2 is k equals 5. And so if we replace k with 5, the result is a continuous function. For any other value of k, this would be an example of what's called a removable discontinuity. A removable discontinuity is a place where the limit of a function exists at a point, but the function value doesn't agree with that point. The reason why it's called removable is because it means that you can redefine the function f at that point to make it continuous. And that's essentially what this example was trying to illustrate, was that we could redefine this function or pick a value of k, which is the function value at the point x equals 2, to make it a continuous function. So we kind of removed the discontinuity that it would have had otherwise. And that's it for this example on trigonometry. If you want to try a few more examples of computing limits, you can check out some of my other tutorials on this topic. And we'll see you next time on Trigonometries.